Bernstein Vazirani algorithm, which is all right. So I think it's working now. Okay, so today we will
Yes, it's
discuss
working.
Bernstein Vazirani algorithm, which is essentially Diet-Souza algorithm, but with a different phase oracle. So the problem is this, that suppose you have access to a black box which implements a function f of x in such a way that it has a secret bit string s. Let me show that bit string s as s naught, s1, sn minus 1. For example, as an example, let's say this s is 1101, something like this. So it has a secret bit string, and when we give it some input, let's say x naught, x1 all the way to xn minus 1, what it does, it gives at the output uh, a function like this. So minus 1 power f of x into x. So it implements a function f of x, which is the product of x, which is the input, with the secret bit string. For example, if your x is 0 1 0 0 0 1 0, so when I multiply this x with s, I will get 0 into 1 0 plus 0 into 1 0, 1 into 0 0, 0 into 1 0 equals 0. So which means that 0 1, the input 0 0 1 0, this state will be translated to 0 0 1 0 because f of x is 0 for this x. So at the output we will get this state. So if we have, let's say, input is 1 1 0 0, so then it will multiply this input x with this secret bit. The secret bit string is fixed, so 1 into 1 is 1, 1 into 1 is 1, 0 into 0 is 0, 0 into 0 is 0. So if I add it modulo 2, 1 plus 1 is 2 and modulo 2 is 0. So which means that at the output, this 1 1 0 0 will still transform to 1 1 0 0 because f of x is 0. So this black box phase oracle implements this function f of x such that the input x is multiplied with a secret bit string, and that bit string is something encoded in this black box, and at the output we get minus 1 power f of x into x. And our job is, our goal is our problem is to find this secret s. So classically, if we have this bit string of 4 numbers, we need at least 4 queries of this phase oracle to be able to find what this bit string is. For example, once I can send in 0 0 0 1, and next time I can send 0 0 1 0, and then I can send 0 1 0 0, and then 1 0 0. So with this 4 different inputs, I will be able to find out what the secret bit string is. And if this bit string is 10 digits long and our input is 10 digit, so I will need at least 10 queries of this phase oracle to find this secret bit string. And Bernstein Vazirani realized that using Diet-Souza's algorithm, but with this function, they can find this secret bit string in just single query using the Diet-Souza algorithm. So everybody understands the problem. We have to find the secret bit string, which this function uses to multiply with the input and add the individual terms modulo 2, and whatever is the output, it raises minus 1 power f of x and multiplies it with the x. So since f of x is either 0 or 1, so it means either x goes to minus x or x goes to x, depending on f of x. So this is the problem. So let's see the circuit for that. And circuit is fortunately the same that we have studied, that you initialized your input to 0, 0 state, you apply Hadamard's, and then you apply your phase hierarchical, and where f is now this x dot s, and then when you get the output of the phase oracle, you take the Hadamard's again, apply the Hadamard's again, and then you apply the measurement operation here in the computational basis, and whatever the output is now classical, this output is actually the secret bit string S0, S1 all the way to Sn minus 1. And we will see now how this is true. I see there is some comment in the chat. Oh, should we? Okay, thank you. All right, so let's start our analysis. So in the 0 step, our input state is 0, and just to remind you that this 0 means that 0, 0, 0, that all bits are set in the 0 state, which we can also write at 0 tensor n. Okay, so in the first step, we apply the Hadamard gates to this state, and this will result in 1 over n square root x from 0 to n minus 1, where this capital N is 2 power n minus 1 power x dot 0 into x, because we have seen this, whatever this state is, this has to be multiplied with this variable x and added over all this to work out the correct sign. But since the state that we're applying Hadamard is 0, so x dot 0 is 0, so minus 1 power 0 for all x is 0, so this goes away, and we have 1 over n sum over x. So we have a nice superposition of all possible combinations of the qubits in a uniform superposition. So let's now apply the phase oracle. So the phase oracle, when applied to this psi1 state, will result in 1 over n square root sum over x. Uf goes to this x, and this will be 1 over n square root sum over x minus 1 power f of x, and f of x this time is minus 1 power x dot s, where this x dot s is defined in a special way, that we multiply the corresponding bits and then we add modulo 2. So x. So this is our state of after applying the oracle. And let's now go to 3, and hopefully after this algorithm you will also see that why do we use phase oracles in many algorithms. And actually it's simply because of this Hadamard transform. When we apply Hadamard transform, our states is of this form, minus 1 power something, and a phase oracle also does something like this, that it multiplies the input with minus 1 power something. So this makes many algorithms work by having phase oracles, that we implement functions in a special way using phase oracles instead of just implementing the function as it is, that we have some f of x and we just work with the value f of x instead of minus 1 power f of x. Okay, so let's apply Hadamard's again. So psi 3 after Hadamard's is Hadamard's on psi 2, and psi 2 here will be x minus 1 power x dot s, and Hadamard's come right here an X. Now the output of header mod would be -1 power X dot S. So this is nothing but 1 over n square root, sum over sum, k from 0 to n, and -1 power k dot x, because this input state is now x, so it will be k dot x. This is not 0, so I will need to keep this k dot x into k. So we sum over all k combinations, but their sign will be decided by -1 power k dot x. Okay, now let me, this 1 over n square root, 1 over n square root becomes 1 over n. And let's take this sum over k out. And we have something inside as sum over x -1 power x dot s and k dot x. They will add together in powers, and I can take x common, and I have s plus k inside into k. So this is, the state at the output after applying a second header mod. Let me show you the circuit again here. So we had header mods, we had phase oracle, header mods again, and now we are at this stage that we are at side 3. And let's just see that if we can work out what side 3 is. So this is my side 3, and we can note, one thing from here, that this term, this is the coefficient of each k state in this sum k divided by 1 over n. So let's see what this coefficient is. So this coefficient -1 power x is something like this. So this coefficient sum over x -1 power x dot s plus k is, I can conceptually expand it like this: -1 power 0, 0, let's say for 3 qubit, into s plus k plus -1 power 0, 0, 1 into s plus k, and so on. So for all combinations of x, we have to take it -1 to power that combination into s plus k, and then we have to add all of these terms, this one, and all of the terms. And let's see now s plus k. So this s plus k is like this. This is a modulo 2 sum. Suppose our secret bit string s is 101 for the sake of argument. So 101 is the secret bit string. So it means that and this k could be something. Let's say we are talking about the first term when k is 0, 0. So when k is 0, 0 and s is 101, so 101 plus 0, 0, 0 will result in 101. And now this 101 will multiply with 0, 0, 0 and will result in 0. And this sum will become, the first term would be -1 power 0, because 0 into 1, 0 into 0, 0 into 1. So we have to add all zeros. And next time -1 power. So again, this s plus k is still 101. So 0 into 1, 0, 0 into 0, 0, 1 into 1, 1. And now this will be 1. The next term would be something. And you can work out and you will see that half of the time it is 0. And for the other half of the time it is 1. So it means I'm adding -1 power 0 and -1 power 1, with half of them negative and half of them +1. So it means this sum will return to 0. So it means that if the secret bit string is 101, the coefficient of the first term in this grand sum is going to be 0. So let's now go to 001. So when k is 001, the next term, so we have this secret bit string still 101. So 101 plus 001 will be, so now when k is 001, secret bit string is still 101. So s plus k would be 0 plus 1, 1, and 0 plus 0, 0. So 0 plus 1, 1, 0 into 0, 0, 1 in 1 plus 1, 2, which is modulo 2 is 0. So this is now 1, 0, 0. You can again check that for half of the time, the power would be 0, and for the other half of the time, power would be 1 when you iterate x all the way from 0 to n minus 1. So when you add up over all the x, you sum to 0. So it means for all k's different than s, we will be getting half of the time 0 and half of the time 1. So the coefficients are 0. But let's see what happens when k is equal to s. So for that term's coefficient, when s is equal to k, that is that s is 101 and k is 101. So 1 plus 1 is 0, 0 plus 0 is 0, 1 plus 1 is 0. So I have 0, 0, 0. So when I have this, then sum of x minus 1 power x dot 0, 0 will be x minus 1 power 0 will be sum of x of 1, which is nothing but n. So sum of 1 over when x goes from 0 to n minus 1. So the sum is n. And we have 1 over n here. So for that term when k is equal to s, this sum comes to n. So n cancel with n, and my state psi 3 is actually nothing but state s. So it means that at the output here, this psi 3 is actually the state s. So when we measure, we will get this bit string s0, s1 all the way to sn minus 1. Okay, so any question regarding this? All right, so I'll show the implementation a little bit later, but let me now discuss the second important thing that I was talking about initially, and that is how to construct phase oracles of that implements various functions. And also how to construct a circuit, that implements, for example.
Sir, sorry to interrupt, but there's a question by Madiha. She says that please repeat the last step, the final output.
Okay, so I know it's a little bit tricky, and the truth is I'm going to repeat it, but you will really get a confidence if you work it out for some of these situations yourself. But let me start again.
I know that we get an answer for s equals to k only. I understand that. But when s equals to k, what is s? S was the final output, and we were dealing with k. So are we saying that the final output is k, or I'm confused about that? If s is equals to k, then what would happen?
So when s is equal to k, it means in this sum. So remember, this is a series where we are adding lot of term, and k is first 0, 0, 0, and then k is 0, 0, 1, and this is some coefficient of all of those terms. So in this sum, let me actually write it again somewhere over here. So the situation is like this, that we have some coefficient, k is this, and then we have some coefficient, and k is now this, and then we have some coefficient 0, 1, 0, and so on. All of these coefficients are 0 when k is not equal to s. So it means, and when k is equal to s, this coefficient came to be 1. So it means at the end, we will have only that coefficient 1, and only one term would be left for which k was equal to s. So that's why I wrote that psi 3 is actually s.
Okay, got that, sir. Thank you.
Okay. All right. So, okay. So let's now see how we can construct different phase oracles. Okay. So for constructing different phase oracles, the ubiquitous tool is a C0 gate. And let me, start. Let me review the C0 again, which I'm sure that most of you are now very familiar. So let's say this is the gate. So by definition, this gives us this x over here, and this y is transformed to y plus x, symbolically speaking. And I can write it like this as well, that cx, when it is applied to xy. Okay, some people write this is called a control qubit and this is called the target qubit. So I'm writing control first and target later. In Qiskit, you write target first and control later. And various books, switch it as well. Anyway, so I'm writing control bit qubit first and target qubit later. So when the CX applies to this, so we get, in general, I can, write it like this. So this is what it means. But let's, take some specific examples like this. For example, if your control is 0 and your target is 0, you get this state. And if your control is 1, your target is flipped. So control remains 1 and target goes to 0. But if your control is in superposition state, so we have a situation like this. For example, what is the control x of this thing? That my control is in superposition state and my target is something like, let's say 0. So to work it out, we will have to explicitly work out this plus state like this. That plus is 1 over square root 2, 0 plus 1 into 0. And I can write it cx 1 over square root 2, 0, 0 plus 1, 0. And now we apply this thing. So this is 0, 0. So this will remain 0, 0. So this control is 1. So target will be flipped and I'll get 1, 1. And this is the entangled state, which we had labeled psi 0, 0, the Bell state. So it means if your control is in superposition state, you get an entangled state. So that's why, we can get entanglement circuit written like this, that when I applied Hadamard on this 0, this becomes plus, and then I apply a C naught on, let's say this is in 0 state. So at the output, I get this entangled state psi 0, 0. So if your control is in superposition, you get entangled state. But what happens when your control is not in superposition, but your target is in superposition? Let's now see that. So suppose we have a situation like this, that I'm applying C naught on a situation like this, that my control is 0, but my target is in superposition. So let's work it out. Cx, so this will be 1 over square root 2, 0, 0 plus 0, 1. So now when the Cx is applied, this 0, 0 will remain 0, 0, and this 0, 1 will become 0, 1, because control is 0 here, control is 0 here. So nothing happens, and I can factor it out again. So I can take 0 common from left side, and on the right side, I'll get 1 over square root 2, 0 plus 1 again, which means that I get 0 plus. So since control is in 0 state, nothing happens to target anymore. Similarly, if I apply Cx to 0 minus state, I get 0 minus back, because control is in 0 state. But now let's see what happens to this situation. That my control is in 1 state and my target is in plus state. So in this case, I get Cx applied to 1 over square root 2, 1, 0 plus 1, 1. So control 1, target flipped, 1, 1. Control 1, target flips, 1, 0. And I can take this 1 common from the left side. So 1 tensor 1 plus 0 over square root 2. This is nothing but still plus state. So I get 1 plus. So 1 plus goes to 1 plus. Nothing happens, even if my control is in 1 state, because superposition is prepared in such a way that it's a positive combination of 0 and 1. So 0, 1 both flip. So it still remains 0 plus 1. But let's now see what happens to this one? So I have Cx applied to 1 minus state. Now in this case, so 1 over square root 2 Cx to 1 0 minus 1 1, and now when Cx is applied, I get 1 1 minus 1 0, and if I take 1 common from the left side, here I'm left with 1 over square root 2 1 minus 0, and I can take negative common, so minus 1. So here we will be left with 0 minus 1, which is the minus state. So now 1 minus state has gone to minus 1 minus state. That I have introduced a phase which is equal to minus 1. And we can think of this phase as with 1 or with minus 1, it doesn't matter because it's a global phase in this case, if this is the only input. So similarly, if we have operation like this, 0 minus 1, this will remain 0 minus 1 because this is in 0 state. So it means that if we have a circuit like this, that I initialize this to, let's say, 0, and apply an X gate, and I apply a Hadamard gate, and then I have some control here. So now this X and H will make it a minus state. Okay, so now this is a special situation, because if this control is 0, I will get 0 here, and if this control is 1, I will get minus 1, and this minus state will go to minus state. So this is this C naught gate with a target set in a minus state actually works like a function minus f of c, because if c is in 0 state, f of 0 is 0 and minus 1 power 0 plus 1, so I get c back. And if this c is 1, so f of c is implemented such that if this c is 1, f of c is 1, and I get minus sign. So we can generalize this to make more general phase oracles using this C naught gate. Okay, let me give you another example. Suppose that you want to work out a function like this. Okay, instead of this, let me work out, give you a circuit, and then we can work out what it does. Suppose we have a circuit like this, that I have one C naught here and one C naught here. So this is my X, and this is my sum minus 1 power f of x. And let's work out what this f of x is. And for that, let's work out what the output is going to be for different x inputs. So if this is your input, let's say 0 0 0 1 1 0 1 1. So let's see how it works. So if this is 0, this is 0, nothing happens here, nothing happens here, and I get 0 0 here. If this is 1 and this is 0, then this C naught will work, and I will get a minus sign at the output. So it means if this is 1, the top one is 1 and this one is 0, so this C naught is not working. So this one C naught will give me a minus sign with this minus minus thing. So I will get minus 1 0 state. So similarly, if this is 0 and this is 1, the other C naught will work and I will get still 1 0. But if they're both 1, this is 1, this is 1.
Excuse me.
Mm-hmm.
Sir, sorry to interrupt, but can you please name these qubits instead of pointing this and this, because we are having trouble to look which
okay.
actually you are pointing toward.
Thank you. Let me, so it's very difficult to switch from teaching on a blackboard to teaching on this tablet. Anyway, so let's label this x naught and let's label this x1. And now I can, say this is x naught and this is x1. So when x naught is 0 and x1 is 0, when they're both 0, both of the C naughts are not working, which means nothing happens to minus state. So my 0, 0 output goes to 0, 0. And when either one of them is 1, so it's either 0, 1 or 1, 0, one of the C naught will work, and we will get a minus sign with this minus state, which we can think of as a minus sign with the top two. So 0, 1 or 1, 0 transforms to minus with minus sign. But when both qubits are in one state, both C naught will be acted on. So the minus 1 will first go to minus minus, and then they will go to minus square. So at the end, we get only minus state. So the 1, 1 will be transformed to this thing. So this is essentially an f of x that works like this. That this is an f of x that when it is 0, when x is 0, 0, or x is 1, 1. And this is 1 when x is either 0, 1 or 1, 0. So we have been able to implement this function. But I actually did it in the inverse fashion. I just gave you a circuit first, and then we worked out what f of x implements. But let's say we want to work out a circuit that goes in reverse, that we specify an f of x, and we want a circuit that implements that f of x. And I hope that you can begin to see how to do that. Suppose I want to have a circuit like this. F of 0, 0 is 0. F of 0, 1 is 0. And f of 1, 0 is 1. And f of 1, 1 is 1. So what circuit will implement that? So we note that here that this first qubit, when it is 0, we get output 0. And when the first qubit is 1, we get output 1. And it doesn't matter what the second qubit is. So this means that, I can very easily have a circuit like this. So if I prepare this Encilia qubit that we call Encilia, so we are implementing C naughts on this. So this is, let's say, the first qubit x naught. This is the second x1. And all I need is a C naught with respect to the first qubit. And that's it. I don't need to do anything to the second qubit. So this circuit actually implements a phase oracle with this function. And we can check, because when the input is 0, 0, nothing happens and the output is still 0, 0. When the input is 0, 1, nothing happens and output is still 0, 1. So it means that 0, 0 and 0, 1 states transform like this. So 0, 0 goes to 0, 0 and 0, 1 goes to 0, 1. But when the first qubit is 1, the C naught is acted on this minus state, and we get minus 1, 0. So similarly for 1, 1, which is equivalent to minus 1 power f of x, x.
Sir, or we could just send x0 as output.
Sorry,
we treat why don't we treat x0 as output, because its output is x0 all the time. So should not we treat x0 as output instead of making a circuit?
I'm sorry, I don't get your question.
Sir, there are two inputs, x0 and x1, and output is all the time what the x0 is. So why don't we treat x0 as output? We take a wire x0 and label it as output.
I'm not sure still of your question, but let me try to see what you're perhaps saying that, let's say this is the input x, and this is also present at the output here. So why don't we just call that this x is output instead of saying minus 1 power f of x into x is output? Is that your question?
Yes, sir. Yes, this is my question.
Okay, so the answer is this. Suppose when you have only inputs set in this computational basis that they are either 0, 0 or 0, 1 or 1, 0 or 1, 1, then I don't even need to write anything over here, because I can, easily see right here, okay, this line is right going there, this line is going there. Okay, they are controlling some operation on something which is not even part of the circuit, that we won't actually even be doing to anything. So why do we say that there is something like, happening to this? So, and that's actually an important question, and it takes, a little bit of effort to wrap your head around it. And let's see how we can do that. So the first thing to do that is that we can say at least one thing. When we have a constant multiplying two, qubits, we can think of this constant with either this one or that one. It doesn't really matter because they are product state. And even if it is with this or that, it's the same. So instead of, treating x naught, x1 and minus, and then we have this minus phase that is coming at the output, we can, think of this with this, or we can think of this with this. So if we have an input which can be written as a product state like x naught, x1, then it doesn't matter. But let's see what happens if we have an input in a superposition state. Suppose you are giving input here like this, that we have x naught, x1, and this minus state as something like this, that this x naught, x1 is let's say 0, 0 plus 1, 0 into minus 2. Now if we work out, we will see that this and this, they give a minus sign, and this and this, they give a plus sign. So when there is a, this circuit, this whole circuit is applied to this state, we get, so let me call it some operator u. When this is applied to this x1 minus, we actually get this thing, 0, 0 minus 1, 0 minus, because we can still factor out minus state from these, but this minus sign will stay with this thing. So now we can clearly see that nothing happens to this, but this state is being multiplied with minus sign. Does that help?
Yes, sir. Sure. Thank you.
Okay. All right. So I gave you a circuit that implements a function that we want. But let's say you actually don't want to do this. You want a flip thing, that we should get 1, 1 here and 0, 0 here. So for that, we can easily do that. I can add an X gate here and an X gate here, because my control is still with respect to the first qubit. I see that this is 1, 1 independent of the second qubit. This is 0, 0 independent of the second qubit. So it means I don't do anything to the second qubit. But now when the first qubit is in 0 state, I should get 1. So how can I do that? I can apply a 0, an X gate after the input. So when this 0 passes through X gate, it becomes 1. So when this is 1, this, C naught is activated, and we get a minus sign, which is equivalent to evaluating f of 0, 0 to 1. But whatever is the input here, I have to get the same thing at the output, because it's a phase oracle that I'm trying to implement, that I should get the same output as the input. The only difference would be that I could get a plus or minus sign according to some f of x, because I'm transforming x to -1 f of x into x. So because of this thing, I have to apply x again to go to 0 state. So this way, I still get a phase oracle, but now my control is reversed with respect to 0. All right, so let me work out another phase oracle. Suppose that I want to implement a phase oracle for the Bernstein Vazirani algorithm with a secret bit string of 1, 0. Okay, so if this secret bit string is 1, 0, my f of x should be 0.10, and this 0 into 1 is 0, 0 into 0. So this is 0. And when my, sorry, this is a little bit confusing notation. So let's write it here. So when x is 0, 0, so f of x, which is s dot x, so let's multiply the 0, 0 with 1, 0. So I will get 0 into 1 plus 0 into 0. So this answer is 0. So for the input 0, 1, when the 0, 1 multiplies with 1 and 0, 0 into 1 plus 1 into 0, still 0. For 1, 0, 1 into 1 is 1, 0 into 0, 0, I get 1. And for 1, 1, so 1 into 1 is 1 plus 1 into 0 plus 0, so 1 plus 0 is 1. So this is f of x. So it means that this x now minus 1 power f of x into x will be 0, 0, and this is 0, 1, and this is 1, 0 goes to 1, 0 with negative sign, and 1, 1 goes to with negative sign. So it means I now need a circuit that transforms 0, 0 to 0, 0, 0, 1 to 0, 1, but 1, 0 and 1, 1 should go to 1, 0 and 1, 1 with negative sign. So this tells me that there's a control over this first qubit. So this circuit, actually this turns out to be the same thing that we just discussed in the beginning. So this is the one that will implement this phase oracle with this bit string. Similarly, you can actually work out very easily. If your control, you have to figure out that where the controls are. Controls are sometime opposite direction, that when the bit is 0, you want 1, and when the bit is 1, you want 0. In that case, you can always implement an X gate before and after the control. And when you don't want, you want the direct control, then you don't implement the X gate. And in this way, you can construct phase oracles for the more complicated situation as well. Okay, so is there any questions, or should we go to the notebook to see its implementation? Okay, so let me save this thing. So I have already sent you this notebook. This is labeled lecture number 4. So it is this one. Sorry, this is a hangover from the other course that I was teaching. Anyway, okay, so let's start with this import of execute quantum circuit, histogram, etc. And this time I'm not going to execute this constant oracle and this oracle that we prepared for the diet Joza. And now you see that even this diet Joza oracle is constructed just like the way I was talking about. This Q3 bit is the ancilia qubit. This is not going to be used in the main function. And this X and H is just there to turn the zero initialized state into minus state. And then there are these two, C naughts. So this is X before C naught and X after. This is X before and after. So implement different types of, functions. Anyway, so I want to go to, okay. This is the input number 10 is the Bernstein Vazirani algorithm. And let me walk you through this. So these first two lines are the usual imports. And I'm using this NumPy package from Python to do some numerical computations. And the secret bit string that we are going to implement in this case is this 101. And there is this n is equal to 3 is the number of qubits. And now I'm defining this Bernstein Vazirani circuit as 3 plus 1. And now you can see why it's a 3 plus 1 circuit. I need additional 1 to prepare to have an Ancilia qubit to implement my phase oracle. So this is usually the case in those circuits where we need a phase oracle to have one extra qubit for that Ancilia qubit. And I have n classical bits, so 3 classical bits. All right, so as always, I start with a Hadamard on each qubit. So for I in range n, which means that I goes from 0 to n minus 1. In Python, the indexing automatically starts at 0 and goes to the maximum minus 1. So on this circuit, I implement the Hadamard on each qubit, and then I'm just implementing this barrier, for visualization. And this is the initialization of the Ancilia qubit. In Python, just to repeat, in this Qiskit, every qubit by default is initialized to 0 state. So you have to make any state by assuming that it is initialized to 0 state. So I'm now preparing this Ancilia qubit in minus state by having X and H. And now once I have this, so this thing, just implements my my phase oracle. All I'm doing is for any q which is 1, when it is 1, so this is the bit string S101. So I'm just sweeping through this bit string because we just saw that if the bit is 1, we need an CX gate. And just so you know, this is the Python indexing. We can also go in the minus direction. So the indexing in Python happens in 2 ways. So if you have a string, let's say A, B, C, D, E, so you can either index it 0, 1, 2, 3, 4, access it like this, or you can also index it. This is minus 1, this is minus 2, minus 3, minus 4, minus 5. And you can, sweep this way, or you can sweep that way. So there are 2 ways of addressing different, strings in vector objects in Python. And string is a vector object. So anyway, so in this case, I'm going from n minus 1 with a step of minus 1. So we're starting from the last qubit to the first one. If we want to, correspond this 1 to qubit 0 and the last one to qubit, the last qubit. You can also sweep in the direct way, but then you will have to think that the ordering is in the reverse way. Anyway, so I'm just implementing this control X gate on a fixed, target n. So n is fixed. This is the n is equal to 3. So this is the 4th qubit, because when n is equal to 3, by default, since the qubit addressing it 0, 1, 2, 3, so the 3rd qubit is actually the 4th qubit. So it's being addressed by n is equal to 3. So target is fixed to n is equal to 3, and the control is changing q. So whenever there is a 1 in the bit string specified, I am automatically preparing a phase oracle with this. Okay, and then I have a barrier, and then Hadamards again, and then we have these measurements on the quantum qubits I, and putting its result to this ith classical bit. And then I'm drawing the circuit. So let's use this MPL to make circuit look a bit better. So now, so this is the Hadamard, and you see this is Q3 is the Ancilia qubit. Can you see my cursor as well or not? This pointer that I'm pointing out.
We can see that.
Okay, perfect. So this XH is preparing the Ancilia qubit, and then I have this secret qubit, secret string implemented through these 2 C nodes. So this is the phase oracle part, and then Hadamard, and then 3 measurements. So you see, we don't do anything to Q3 after implementing this phase oracle. That's now implemented using simulator, and you see 101 has a probability of 1 of measurement at the end. Just as we showed that after these Hadamard, oracle, Hadamard, the state actually transforms to S state. So when you measure, you only find S state. So we had this 101. So this bit string, we are able to find this secret bit string of this oracle in just 1 simulation. So I haven't implemented it on quantum computer because I hope that from the other notebooks you can see that it's a trivial matter. You just copy your token from your account here and load that account, and then you can run it over there as well. Okay, so any question regarding today's session? Okay, so if not, sorry, we can finish today a few minutes earlier, because the next thing that I want to talk about is quantum Fourier transform. But actually, so let's just before finishing up, take a poll in the chat about two things. So number one is there anyone of you who is not familiar with Fourier transform, like the classical usual Fourier transform? And the second thing is that if we plan for the makeup lecture on Monday at 5:45 p.m., is that okay with everyone, or you want to do one on Friday at 8 p.m.?